Swayam Prabha. Digital India. Educated India.
Welcome back, students, to the final lecture of this module, viscous fluid flow, where we are deriving the Navier-Stokes equation. So in the last lecture we wrote the general deformation law for Newtonian viscous fluid, okay, and this equation we call it equation number 18. So proceeding forward, so we will talk a little bit before writing the Navier-Stokes equation. We will talk about the difference between the thermodynamic and mechanical pressure. So do you think they both are same? No, they are not. So mechanical pressure, so the pressure that we derive, we find out using the Navier-Stokes equation or any other such equation, is the thermodynamic pressure. So the mechanical pressure P bar is negative 1/3 of sum of 3 normal stresses. All right. What are the 3 normal stresses? Tau xx, tau yy and tau zz. So P bar can be written as minus of 1/3 tau xx plus tau yy plus tau zz, or it is written as lambda plus 2/3 mu divergence of V, and this is equation number 19. If you substitute the value of tau xx, tau yy and tau zz using the previous equation, this is what you are going to get. Okay. So what does this mean? This means that mean pressure in deforming viscous fluid is not equal to thermodynamic property called pressure. Okay. However, if we want both of them to be same, two different ways, right? One is, if you look at the above equation, P bar will be equal to P if either lambda plus 2/3 mu is equal to 0 or divergence of V is equal to 0. So let's say is equal to 0. Actually this is called Stokes hypothesis. All right. The second way is divergence of V can be, if it is 0, then also this is possible. This is possible. This is more commonly possible because divergence of V is 0 for incompressible flow. So that is when we deal with water and hydraulics, you see all the time we assume incompressible flow. So both the mechanical pressure and the thermodynamic pressure, they are same, but in general it is not true. Now coming back to the Stokes hypothesis, it says even in case of compressible fluid, if lambda plus 2 by 3 mu is equal to 0, then we can have. However, the experiments indicate that it's rare. So lambda is generally not equal to 2 by 3 minus 2 by 3 mu. So Stokes hypothesis is not satisfied, since lambda is usually, and the reason is lambda is usually positive, okay, and bulk mu we haven't heard it is negative. So that's why lambda plus 2 by 3 mu is equal to 0. The Stokes hypothesis is rarely satisfied, okay. All right. So now going back to the objective of this module, the Navier-Stokes equation. Okay. So desired momentum equation for general Newtonian viscous fluid is obtained by equation 18, that is the deformation law in Newton's law, rewritten Newton's law, which was equation number 9, and the result is famous equation of motion called as Navier-Stokes equation. So it is rho dV dt is equal to rho g minus delta p plus del j of mu Vi all right. This is equation number 20, and now we have written general Navier-Stokes equation. All right. All right. So after we have written this Navier-Stokes equation, it also makes a little bit sense to see what happens with the incompressible flow. How does this equation modify in case of incompressible flow? So to do that, we go to a fresh page. So incompressible flow, what is that? If rho is that means incompressible flow, that means divergence of V is equal to 0. So if you look at the Navier-Stokes equation above, this will be 0. This the last term, divergence of V. All right. all right. Therefore, in equation 20, if we assume mu is constant, okay, as well, because in most of the hydraulic purposes we assume mu is constant, then we get Navier-Stokes equations for that is rho g minus delta p plus mu del square v. This is another equation of significance, because when it comes to Navier-Stokes equation for practical purposes, this is the equation that we are going to use. So, one important thing to note is, I mean, we know from before, if rho and mu are constant, then the equations are totally uncoupled from temperature, correct? Right? I mean, that is why rho and mu will be constant, because if we assume constant, then there is no effect of temperature, right? Or if there is no effect of temperature, we assume at a one fixed temperature. Just in case, because if you remember in the beginning we said that the thermodynamic properties, I mean the properties are both pressure, temperature, including the velocities, that we need to find using the conservation laws. We haven't discussed about temperature because this is not relevant to us, so outside the scope of this particular course. But if one desires, one can solve for temperature from energy equation alone, okay. But we have not seen what that equation is. And now moving to the last part, again that is called in-viscid flow. So, actually we are going to study wave mechanics as part of in-viscid flow, because there we will have potential theory and other things. But here in in-viscid flow, the Euler, it's fitting to discuss about, mention Euler and the Bernoulli's theorem, how it has its origin, okay. So, if we assume that viscous terms are negligible as well in equation 21, then Navier-Stokes NS can be reduced to rho dV dt is equal to rho g minus delta p, and this is equation number 22, very famously called Euler equation for in-viscid flow. So, now you see how these equations have come into existence, the base, going to the origin of these equations, okay. A couple of sentences about this equation. So, this equation is first order, right, in velocity and pressure. All right, and thus it is simpler than another change is in viscous fluid flow. We had already been assuming no slip condition, that you have seen also in the boundary layer theory and turbulent and laminar flow. So, at fixed wall, no slip condition must be dropped and tangential velocity is allowed to slip because of the absence of viscous forces. Now, the last point before we close our lecture is Euler equation for steady incompressible frictionless flow. I think I will go to the next paper. Can be integrated along a streamline between points 1 and 2 points 1 and 2 means any 2 points to give Bernoulli's equation. Which is P plus half rho V square plus rho G Z1 equal to P plus half rho V square plus rho G Z at 2. Okay, this is equation number 23, and this is a homework question. Please try to do this at home. So, if unable, we can actually post the solution in the forum. So, from the beginning of this module, you have seen how we have went ahead and tried to from basics, from material derivative and the geometrical properties, talked about the strain rates, the shear strain rates. Then we went into the equation of continuity using the material derivative, then equation of momentum. We saw the deformation laws in the fluids. We derived the Navier-Stokes equation. We also saw the difference between the thermal and the mechanical pressure and the conditions in which both can be the same. Then we simplified our general Navier-Stokes equation which we had derived. That was the purpose of this module. Then we simplified it to obtain the Euler equation, and also how the Bernoulli's equation is got. So, you also know the origin of the Bernoulli's equation in its purest form. So, with this I would like to close down today's lecture. Next week we are going to study a topic that is called computational fluid dynamics, and is a very well continuation of these equations that we have read this week. So, thank you so much for listening to me for this particular module. I will see you next week.